Okay, today we're in lesson 8.1, solving systems of linear equations by graphing. Section 8.1, solving system of linear equations by graphing.
One way to actually find a potential solution is by trying to consider the visualization of these linear equations, namely the lines that represent the graph. Here's a linear system, and I want us to solve it. Y equals x plus 2, and y equals negative 2x plus 5. So how am I going to do this? I'm actually going to graph each of these lines separately and hope I can identify the point of intersection of the two. That point of intersection is the common point that should satisfy both of these simultaneously. Let's give it a shot. Y equals x plus 2. What is that? That's a line that has intercept 2. Y equals mx plus b. So the intercept is 2. And the slope is, well, invisible 1 over 1. So 1 up, 1 over. 1 up, 1 over. 1 up, 1 over. You get the idea. And so on. Okay? So that's the first linear equation. Now let's consider the graph of the second one. So the second one is y equals negative 2x plus 5. So here we have a y-intercept of y equals mx plus b. By the way, not bad to do that. To say to yourself, y equals mx plus b. To remind you, b. That's the y-intercept. That's at 5. And the slope is negative 2. That's negative 2 over an invisible 1. So it's rise over run. Negative 2 is the rise, so it's really a fall. The elevator is going down 2 units. 1, 2, and then I go over 1. Pow! Look at that, by the way. I instantly hit the line. 1, 2 over 1. Let's connect these points. And I can see the intersection pretty clearly. My guess, so I'm not going to now make a guess. My guess is that here's the place where they intersect, which seems to be what? That seems to be 1 over, so x equals 1, and y equals 1, 2, 3. So I'm thinking 1 comma 3 is going to be a solution. Now we can check. We know how to check. We know how to do that. We let x equals 1 and see if y equals 3 satisfies both these equations. If I put a 1 here for x, that's going to be a 1 plus 2, that's 3. That checks. Good. And what about if I plug in a 1 here? I see a negative 2 times 1, that's negative 2 plus 5. Negative 2 plus 5 is 3. It checks again. So in fact, we check this and we can see, yes, by plugging into both the equations, we see that both hold. So in fact, that is the answer. That's the solution. So a neat way of actually finding a solution is by looking at a graph and seeing if you can identify the point of intersection. Now there's another way of thinking about this. Let's take a look at this system. We could actually use the famous graphing calculator to produce the graphs instead of us doing it by hand. Now to do this, by the way, let me just give you a helpful tip because I'm an expert on the graphing calculator. You have questions on the graphing calculator, you come right to me. The first thing is you actually have to have the equations as y equals the stuff. So this one's already set, y equals 1 half x, but that one you actually have to solve for y. So I'm going to add y to both sides, and I see x equals 2 plus y, and then if I subtract 2 from both sides to undo the 2 there, then I see that I've got x minus 2 equals y, and so y equals x minus 2. That's the way to type it in to the calculator. And so let's turn it on, get it warmed up. You want the calculator to warm up a little bit, get it sort of ready to go, because we're going to have some fun with this. And so the first thing we do, here we go. We press the y equals, and then we put in the two functions there. And you can see that I've already actually written in the two functions. Okay, great. And now what's the next thing I do? Well, the next thing I do is I go to the calculator mode here, and I'm going to press 5 because 5 tells us that we're looking for the intersection. And there you can see we produce the graph, so that's pretty cool. And now what I want to do is I want to actually have it solve for us, so we push the enter key once, twice, 3 times the calculator. And you can see there's the answer right there. What does it say? It says x equals 4, y equals 2. And so the calculator does it for us automatically when you can find a solution. And then it's good to check. It's good to check your answer. So when you see that we have x equals 4 and y equals 2, we can certainly check. So I put in 4 for x and 2 for y. 4 minus 2 is 2. That checks. And if I put a 4 in for x, I have 1/2 of 4, which is 2, and that checks. And so you can see that, in fact, this checks. So the calculator is a wonderful way, in fact, one of my favorite ways of playing with looking at these equations. Now, if I could just figure out how to turn it off. There we go. Great.
All right, now we're going to take a look at example 2, solve problems using systems of equations. Solve problems using system of equations.
Okay, so we've taken a look at graphing lines. We've taken a look at graphing inequalities. I now want us to take a look at scenarios where we're actually looking for solutions to 2 linear equations simultaneously. A little bit tricky because we're going to graph a line, then we're going to graph another line, and where those 2 lines intersect is actually going to be the solution that we seek. Let's take a look at an example and see. And actually, this is a fun example. This example involves trains, so I always have to wear my train cap, or at least that's what they tell me. I have to wear a train cap. Let's check it out. I think I look good. Oh, look at this. Very handsome, by the way. Thank you very much. All right, here we go. So a passenger train left Orlando traveling 60 miles per hour. After the train had traveled 100 miles, so after the train has already gone 100 miles, then a freight train started down the same track at 80 miles per hour. Our mission is to graph the system of linear equations that describe the scenario. And then, let's see if we can answer the following 2 questions. How long after the freight train takes off will it catch up with the passenger train? And then the second issue is, what distance had the trains traveled at that point? All right, so let's think about this together. First of all, so we first have a passenger train. So here's the passenger train. Awesome. And then we have a little teeny freight train. Okay, so what happens? Well, the passenger train actually leaves first. Let's see that happen. So the passenger train leaves first. And then after a while, the freight train leaves at a faster speed. And the question is, when does the freight train, everyone calm down, when does the freight train actually catch up with the passenger, and then how long that take in terms of time and also in terms of distance? Okay, so let's think about this together and see if we can make progress on this training question to get us trained for thinking about these kind of equations. So there are lots of ways of doing this, by the way, and I'm going to show you the way that I'm thinking about it. The first thing I want to do is focus on the freight train, because that's, I think, the place I'd like to start. We focus on the passenger train, that's fine too, and our answer would be the same, but just in terms of writing things down, it's going to be a little easier to focus on the freight train. Now, we know that distance equals rate times time. So if I know, for example, that the freight train is traveling 80 miles per hour, then if it travels for, let's say, t hours, I know it traveled 80 times t miles, because distance equals the rate 80 times the time t. So for the freight train, I know that distance equals rate times time. Now, what about for the passenger train? Now, this is going to be a little bit trickier. So distance equals rate times time. So distance equals rate, but rate is, in this case, 60t times time, but we didn't start the experiment at this same moment in time, because remember that the passenger train had a head start. So when the freight train starts, the passenger train is already 100 miles ahead. So the distance is actually 100 more than what it would have been otherwise. So I have to actually add 100. Let me just say that one more time. That when I'm looking at the length of time that the freight train traveled, then in fact the distance that the passenger train traveled is going to be this plus the 100 miles it traveled before we even started the experiment here with the t. Okay, 2 linear equations, and we want to solve them simultaneously. And the way we're going to do that is actually by trying to graph them. So let's actually see if we can produce a graph of these. So here I've got xy. Lots of stuff going on here. Lots of stuff going on. But I think we can handle it. I'm thinking we're going to handle this and handle it quite nicely, as you'll see. Okay, so first of all, the x here is going to represent time in hours. And the y-axis here is going to represent distance. So distance, and that's going to be in miles. And so I labeled my axes so that you can see what this is going to be. And now we have to graph. And so we can graph the lines kind of any way we want here. So for the freight train, we see that d, that's the y, so d equals 80t. So in some sense, this is like y equals 80x. So we see that it intercepts the y-intercept is 0. When t equals 0, d is 0. So at 0, it didn't travel anywhere. And then when t, for example, is like 1, so 1 hour later, d is 80 times 1, which is 80. So 1, we have 80. 2 points, of course, determine a straight line. And so, with my straight edge, I can actually put these together and graph the line. Let's put it together nice and clearly. There we go. And let's graph. Ready? Graph, 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 graph. Graph, 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 graph. There it is. Okay, now what about the passenger train? So when t equals 0, 0 for the freight train, we actually see the passenger train has that 100-mile head start. So when t equals 0, actually, the passenger train is 100. Now let's look at the units here. This is 80, so half of 80 is 40, and half of 40 is 20. So to go 100, it has to go 80 and then an extra 20. So it's right here. So that actually is right there. Let me use a different color. I'll use a different color. And then 1 hour after the freight train leaves, then it's 60 plus 100 is 160. So 1 hour, we're at 160, which is right here. And now if I graph this line, okay, let's graph this line. Oops, make it nice. Make nice with the line. Gotta make the nice with the line. Then what we see here is that very close, and you see there's a point that they cross. That point is right here. We can see it visually, and we can actually read off the graph. Now, of course, we don't know if the graph is really accurate or not, but we can read off the graph, and it seems like the time is 5, and the miles is 400. So it seems as though that they match up, they meet, right, when the two lines cross. And that seems to be at 5 for the time and 400 for the distance. Now, let's check. Let's see if when t equals 5, d is equal to 400 in both of these equations. Well, if I put in a 5 for t into the freight equation, then I see 5 times 80. 5 times 80, of course, is 400, so it checks there. So it checks here. Tick, tick. And then what about here? If I plug in 5 here for t in the passenger train, then I have 60 times 5, which is 300. 300 plus 100 is 400, and distance is 400. It checks again. So there we have it. We see actually it checks, and we've actually solved these things, looking at it, graphing it, and so forth. Absolutely cool.